so David was, he became a specialist in undecidability. He likes, yes, you know this. I think it's more, I would say it's a philosophic point of view. If you just discuss with Stock, is everything may be decidable. Yeah, it depends on your,
No, I just said that you can. Anyway.
Yeah. Anyway. So I would rephrase as follows. David likes to be provocative. Such title, so please do it.
All right. Thanks. Thanks for the introduction, and thank you for coming to this talk. This is a joint work with Dmitry Katz, and let me set the record straight here. This is not a philosophical talk.
No.
This is everything I'm about to say is all theorems and provable. And there is some sort of philosophy surrounding this, so that in that sense you're absolutely correct. But I will discuss it in a narrow scope, and I won't be able to do the justice to the topic of decidability fully here. But in the narrow scope of Skorohod problem, it's all proofs and theorems. But perhaps that's what makes this topic so fascinating, because you can actually prove theorems about things which a priori look fairly philosophical. Perhaps the most amazing thing about the concept of undecidability or incompleteness, Gödel's incompleteness, is that this is not philosophy. This is actually mathematics, rigorous and provable. And all right, so let me begin. I also want to apologize that for some reason the abstract was not uploaded to the program. The title was, and that's not my fault. I did submit it.
But the problem is where to put it. So it's a problem.
But there's other talks did have abstract. Mine was conspicuously absent. So and several. There's actually a few talks don't have an abstract. And it's certainly undecidable. But you haven't missed anything, because if in fact the whole abstract was basically stability of Skorohod problem is undecidable. There's nothing I could say more meaningful than just it. So let me begin. The plan is as follows. I will begin by reminding you, or for those of you who are familiar with this topic, which is already about 50 years old, and introducing those of you who are not familiar into the Skorohod problem. And then I will spend probably at least about 20 minutes, half an hour, sort of giving you a tutorial on the topics of undecidability, because I suspect that this might be the most fascinating part, most interesting part of the talk. Okay, so Skorohod problem, we define it as follows. So we have a matrix, d-dimensional matrix, and we say that we solve the Skorohod problem if we can do the following. Whenever we have a continuous function on the continuous non-negative time, taking values in the d-dimensional Euclidean space, we can find two other functions on the same domain and same range, which satisfy the whole range of constraints. If you've seen these constraints before, if you know what Skorohod problem is, great. If not, this probably looks a bit contrived and strange to you, because why would you want to have something like this? So what is this something like this? We want z and x and y to be related by this first linear equality. We want z to be non-negative component-wise. We want all functions to be continuous. That's the setup. You can extend it, but let's stick with the continuous domain. We want the function y to start at 0, and we want it to be non-decreasing. And finally, what we want is the following relationship. In an integral form, what it really means is the following. Y is non-decreasing, but when y is increasing, z has to be equal to 0. You cannot have these two things simultaneously. All right? So y is a function which sort of stays constant, goes up, stay constant, goes up, but whenever it goes up, z has to be 0. All right? So that's the requirement. So we say that we solve the Skorohod problem if whenever we have a continuous function x, there exists some y and z which satisfy these constraints. Yes? I already made a mistake, probably.
Probably want to start x in the ordinary, right?
I'm sorry?
You probably want to start x.
Yes.
In the
X in the, that's x in a non-negative order. That's right. X of 0 has to be non-negative. ortho, otherwise immediately have infeasibility. Thanks. This is the first time I'm giving this talk. I'm sure I'm going to have lots of typos and errors, and I'm also not an expert in Skorohod problems, so I apologize to the experts in advance. Mistake number one, more coming, probably. Okay, so why would we want to, why are we interested in something like this? To my knowledge, the most relevant, at least to me, application is the application in the theory of queuing networks, specifically in a heavy traffic regime. So you have some kind of a queuing network, and you have servers, and servers are critically loaded or nearly critically loaded. As queuing theorists, we're interested in queues. It turns out that you can think about this queuing dynamics problem in the sense of a Skorohod problem in some appropriate way. So in this case, Z, for example, would correspond to vector of queues, appropriately normalized. But let me not go into details of that. This is not going to be a talk about queuing networks. But you can think of Z as a normalized vector of queue lengths. Hence, it is non-negative. That's why Z needs to be non-negative. You can think of Y as a cumulative idling process in each server J. So Yj at time t is the amount of time that server J was idling up until time t. And you can think of X as something summarizing stochastic primitives, like arrivals and services and routing, for example. So at a high level, the way to think about this is that you know X, that represents the stochastic primitives, and you want to find what's Z and Y, because in queuing theory, specifically, you want to know Z. What's the vector of queue lengths at a given time t, in steady state, etc. Okay? So that's the main motivation. That's one of the motivations to look at the Skorohod problem. Specifically in the context of queuing applications, when you look at the systems in heavy traffic, it's a particularly interesting case is when the input process X is a Brownian motion, say with some drift theta and some covariance matrix gamma, and starting state X, same mistake, or maybe mistake number two, X has to be non-negative, start in a non-negative ortho. Okay? In that case, you sort of describe the problem by a data already, and I want to start start this thinking about this in this mentality of a data in some sense. So the problem data is theta drift, covariance matrix gamma, reflection matrix R, starting state X. Okay? All right, so that defines the dynamics of the process, perhaps, because I never said that this is actually possible to find Y and Z, but we'll get to that. A very much related object to this problem is something which we call a fluid model of semi-martingale reflective Brownian motion. Yes, the top process is called the semi-martingale reflective Brownian motion, and the bottom process is something called fluid model of SRBM. And it's even simpler. You can think of it as a special case of the top process where you simply make a Brownian motion deterministic. So in that case, X, the input process, is just a straight line. So you have a starting point, X, straight line, and you want to find some Y and Z such that they satisfy the set of equalities and set of constraints that I've described in the previous slide. Okay? And in that case, you have one less of a data. You have only starting state X, a reflection matrix R, and a drift vector theta. Now, the fluid model is a completely deterministic question. It's a deterministic object, right? I have a straight line. It's a deterministic object. And I'm interested, can I build Y and Z, for example, that satisfy these constraints? OK, so these are two interesting specific cases of Skorohod problems to consider. And I will focus on this problem, fluid models, primarily. That's going to be the object of interest. I might be going a bit too fast on the Skorohod problem because I want to spend, again, more time. And again, this is something that many of you have seen. What are the key questions we're interested? Here's the list. When can you find Y and Z satisfying these? When can you solve the Skorohod problem? That's question number one. In the context of SRBM, when is it the case that the reflected Brownian motion is positive recurrent? When do you have invariant measure? That's interesting, again, perhaps in the queuing application. So the reflected Brownian motion represents the Q-length dynamics. Perhaps you can link the two, and by solving this problem and figuring out when is it positive recurrent, you can say something about queuing model as well. Perhaps less obvious, but again, a critically important question is the question of when is the fluid model stable? I haven't defined stability of the fluid model, but you can think about the whole range of questions. For example, so you start with, you have a fluid model, you find y and z. When is it the case that the realizing trajectory stays bounded, for example, converges to 0, diverges to infinity? Roughly speaking, we'll say that it's stable if it is attracted to the origin, converges to the origin. But I'll give a formal definition of this shortly. So if this is too loose, don't worry about that. And finally, what's the relationship between these properties? So this is a list of questions that have puzzled people in the community for many years now. And trying to understand this is an important and challenging problem. Let me tell you a little bit of a background of what we know up to now. Let's begin with this existence of a solution. Here, luckily, the answer is relatively simple and concrete, constructive, and is given by the following notion of a completely S matrices. A matrix R is completely S if it satisfies the following property, that for every principal submatrix A, there exists some vector, non-negative vector U, such that the product is strictly positive in all coordinates. You don't need to think hard about this property. All that is important is to realize that there is a simple and checkable condition on matrices to figure out whether it's completely S or not.
What is this?
Completely S, that's a historic.
Stimke.
Huh?
Stimke.
Okay, good. So
Somebody's name.
yes.
You done something?
But yeah, I've learned, of course, I'm,
Me too.
I'm learning more and more. I didn't know. For some, in papers it's called completely S, but I didn't realize that there is a name
How do you
attached to it.
spell STI?
Okay. All right. So as I said, what we want to keep in mind is that this is a simple constructed checkable
Strange.
condition.
I would say what would be completely constructed.
Never mind. strange, not strange. Let's. If we get stuck on this philosophical point, then I won't get far. So let me move on. All right. So why is it an important notion? Because it turns out that reflection matrices which are completely S is exactly give the class of Skorohod problems which are solvable. And this was done in a variety done by a variety of people in a series of papers. And basically, the summary is that a solution of Skorohod problem exists for every input process X, if and only if the matrix R is completely S. Okay? So at least we're done as far as this is concerned. One needs to know that solution need not be unique. You can have multiple Y and Z satisfying the same X. But it's going to be, it turns out, in the context of SRBM, it's going to be unique and low in the distribution. All right. Let me now to discuss the issue of stability, because that's the key issue I would like to discuss today. Let me remind you that the process looks something like this for the fluid model definition of the Skorohod problem. So we have a linear process, starting point X, a linear drift theta t, and we want to find Z and Y which satisfy this relationship, plus a whole bunch of other relationships, which I'm not going to bother to repeat. It's just a set of some constraints. All right, so again, this is a deterministic system. We will say that this model, a fluid model defined by a drift, a reflection matrix R, and a starting point X, is stable if every solution, I have to say every because there's no guarantee of uniqueness, if every solution is such that the Z part of the solution converges to 0. All right? That's the definition. All right? I don't know if you have any questions about it. I think it's rather perhaps straightforward at this stage. I wanted to be careful that to say that the problem is defined in terms of these three parameters here, theta, r, and x. Because let me now also introduce a very much related notion. And let me call it, and here I'm departing, just a second, Maury. I'm departing slightly from the conventional definition and say that, let me say that the fluid model is globally stable if it is stable for every starting point in the non-negative orthant, right? So again, it might be that it's stable from starting from some point, it tracks to 0, and starting from some other point, it does not. In that case, I would call it not globally stable. I want to make a distinction here because most of the talk will be about this property, even though in application you're probably more interested about this property. Maury, you had a question?
Yeah, I'm not an expert in SRBM either, but there's a couple of things that are
No.
potentially a little confusing in that. I mean, I've only been involved for a year, but I mean, the thing is, when we typically talk about a fluid path rather than a fluid model, and the problem is when you say fluid model, you think in terms of fluid model equations, and there, if you use the definition of stable, stable means that you have a uniform stability statement, not just every solution is 0, but there has to be, depending upon the initial data, there has to be a time where all solutions starting from that point are 0 by then.
Okay, so the first point on the model, that's actually, okay, so that's a bit tangential, but I've seen these terms being used and misused in all kinds of ways. So for example, Sasha Stoller believes that you should say fluid model only for the weak limits of the underlying stochastic processes. And I also take the view.
That's called fluid limit.
But he calls it a fluid model. Okay, so, but.
Fluid model is correction.
Yes, Ruth?
I have a suggestion. I think it's undecidable what terminology.
Right, it's undecidable, and let's.
As long as it's internally consistent.
It's
Well,
yes.
you keep going.
Let's just agree that I call the first property stability because I'm going to talk about this property all the time. I don't want to premise it by saying global stability, global stability, global stability all the time. So that's the only reason. When I write a paper, I promise to be as consistent with the rest of the literature as humanly possible. All right. So that's the definition. Let's be just internally consistent. All right. So let's move on. Why is the global stability is relevant, and in fact, perhaps more relevant than just the stability from a given starting point in the non-negative orthant, because whenever you have a global stability, as was established by Paul Dupuy and Ruth Williams in '94, whenever you have a global stability, it turns out that the underlying semi-martingale reflective Brownian motion, SRBM, is positive recurrent for every covariance matrix gamma. And I think, is it accurate that for every correct?
You need non-degenerate.
Non-degenerate, yeah. Otherwise, you might not have a uniqueness of this.
You might not go every.
Right. So at least you have this one directional connection. Okay, so therefore you have this very important link between the fluid stability of the fluid limit, fluid model, and the SRBM. Naturally, the question is whether the converse is true, and we already heard recently Maury's talk in stochastic networks that if you go in dimensions 6 and higher, then the converse is not true. You might have an example where system is not globally stable, yet SRBM is positive recurrent, right? And I guess if you have any questions about these two results, feel free to ask Maury and Ruth, but not me, about details of these connections.
Wait, in your example, is for any x, there is no stability.
I mean, the definition of
So do you have one, is it true that in
well-
all paths diverge to infinity, or you have one particular path which diverges to infinity?
Well, okay, the thing to look at in particular is to look at a linear fluid path. You come up with some that are not linear that also diverge. But it depends on the initial point. You know, it also, the thing is you can have bifurcation. So I can come up with some that don't diverge just because they said it's 0.
Okay, all right. So there is a link, but it's not one-to-one link. However, when you go, when you restrict your model to be three-dimensional, at most three-dimensional, there is a direct link saying that one model, SRBM is positive recurrent if and only if the fluid model is globally stable. This was, part of it was resolved by El Karoubi and co-authors in 2002, and recently this connection was nailed by Brown-Sandai and Harrison. But this is this is important because not only it gives you complete connection, it turns out you can completely characterize globally stable fluid models in dimensions 3. So not only you have a link, that's actually, the link is constructive, and let me tell you what it is. Now, I give you all these details precisely because they are not important for my talk. It's just to give you sort of, convince you that this is something that you can indeed check and program, and therefore this gives a constructive conditions for stability. It turns out that your fluid model is globally stable if and only if the following is true. You compute the whole bunch of parameters like beta 1, beta 2 straight from the data of the model, from thetas and r's. So in some simple algebraic way, you introduce some regions of theta and r defined by a set of inequalities in a fairly explicit way. And it turns out that exact stability conditions are determined by the following diagram. So you just have to go and check a few cases. First, you check, is it true that r inverse theta is less than 0? It's not true, turns out the model is unstable. If it is true, then you have to check, is the theta part of this region that I just described before, something like this region? Okay, if it is true, then you have to check, is it true that the beta, which I also defined in the previous slide, less than 1? Yes, then it's stable. No, it's unstable. If that's not the case, then you have to check something else, which is something to do with linear complementarity problem. And again, that's you can solve this. You need to look at this system and see if you indeed can find two vectors u and v satisfying the whole bunch of explicit inequalities and equations. And if you can, then its system is unstable. If not, its system is stable, right? So it is important to keep in mind that in this case, you have a complete and accurate and constructive characterization of stable Skorohod problems, globally stable Skorohod problem and positive recurrent SRBMs, because those are linked in 3 dimensions. And I'll come back to this diagram because this will serve a certain purpose later for me. Do you have questions or comments? So let me then move on. So now after I set the stage, let me state the main result. And as advertised, the result is that a stability of the fluid model, not a global stability, stability of a fluid model, when the starting point is a part of the data, is an undecidable property. Namely, there does not exist an algorithm or computational procedure which on this input, problem input, outputs yes if it is stable and outputs no otherwise. This is phrased a bit strange, and the rest of the talk will be an effort to sort of demystify why did I say yes and no and so on. Do you have any questions other than what's undecidable? Because that's going to be the question I will be answering from now on. But other than that, yes, John.
Do you assume that the input is a rational number?
Yes, indeed. For the theory of decidability and computability, because it's a theory about Turing machines, etc., we assume that all the data inputs are rational. And that's because it's a negative result. This is sort of is not restrictive. It's actually a strength, not a limitation of this, because it says that even within a domain of rational inputs, you cannot solve this problem in some appropriate sense that I'm about to explain. Other questions?
Does X enter into this in any serious way? Like, for instance, if you say that there's a given X,
Given X.
if there's a fixed X and you're looking.
That will be a part of the explanation. I have to explain what does it mean. Is it a given X and so on? But jumping ahead, what it means is that when you look at the space of inputs, a combined of X, theta, and R, the classification of stable versus unstable cannot be done by any constructive ways. It doesn't mean that you cannot exhibit a particular case, X, theta, and R, which would be, which you will be able to solve, stable or not, because I can construct some simple, silly examples where you can solve explicitly. But I'm saying for the whole class, you cannot construct an algorithm which solves it for the whole class of instances, and that's something that's the core of the statement, and that's something I want to get next. Yes.
But you're not. But if you restrict R to a certain class of matrices, then it may be decidable, right?
Of course, of
So
course.
you're saying that is too many.
That's too many. For example, yes, if you have this what is called the P matrices, which come from, yes, of course. But by the way, I didn't say explicitly, but R is completely S. That's part of the assumption. Otherwise, it's not even interesting. Yes.
The algorithm must be finite, yeah?
I'll talk about algorithm computability.
Okay?
Huh?
Countable is okay?
No, I'll get to that. I'll get to that. There's no notion of a countable algorithm. Algorithm has to be finite, has to finish in a finite number of steps.
But anytime if you have
I'll get to that. So again, questions other than yes. Let me start there.
Do you have any a priori knowledge about the characterize the stable X from the unstable?
A priori knowledge?
You know, like topologically, how do they look like?
No. In fact, what this is saying is basically there is no constructive characterization of this. You might be able to say something like some statement about, I don't know, monotonicity or things like that, but there's nothing you can say here which will be constructive that I can, so that I can do something like in this way. This I can give to MIT undergraduate. He or she will code it up and give the answer without understanding. MIT undergraduates are smart, but not that smart to to know Skorohod problems. But so the point is that this is there's nothing that is constructive here. But of course, you can come up with all kinds of interesting characterizations. Damon.
In the statement of the theorem, is D fixed but arbitrary?
Good. D is not fixed here, and jumping ahead, we conjecture that even when D is fixed in sufficiently high dimension, for example, I don't know, D is 7, it's still undecidable, but we don't have such a statement. So that's a good question.
So
Yes,
I
more.
was going to ask the same question about dimension, but since, let me ask a little bit further. What happens in lower D? Is something different happen?
In the lower D, well, obviously dimension up to 3 is done. Apart from that, there's nothing we just don't have results about that. It's hard even, I would conjecture that for sufficiently high but fixed dimension, it becomes undecidable as well. But we don't have results proving that. So that's, perhaps 6 is the right dimension.
Are we going to see how the dimension enters in any way?
Yes, hopefully. Yeah.
yeah.
Yes. Well, in some ways, I won't be able to give all the proof details, obviously, but you will see that enters. It's then I'll get there. Okay, so let me then move on, and let me make a couple of perhaps typical mistakes or sort of misunderstandings that come up here. So first is that it does not mean that there is a particular instance of a Skorohod problem which is undecidable. In fact, such a statement doesn't make sense. So sometimes I'm asked this question: does it mean that there is some particular particular X, theta, and R such that this problem, stability of this problem is undecidable? The answer is: turns out that whenever you talk about one particular instance, such an instance is always decidable for almost trivial regions. And again, that's something I'll try to explain. Decidability theory is always about the theory of infinite collection of problems. So I'll get to that. I think that's an interesting and subtle and difficult point to wrap your mind around until you sort of really sort of understand what this theory says. And the second is that this is not, in one of the papers which cited our earlier work, it was said that we proved that the problem is NP hard. This is not NP hard. This is much stronger. NP hard means that you just need to spend exponential of something like exponential time to solve the problem. What this says is that there is no finite algorithm period, regardless how much budget of computation I'm affording you. You can compute e to the e to the e to the e to the n times if you wish, and try to come up with the answer. And I'm saying that even this is not possible. So decidability is this absolutely sort of the limitation of computation period, regardless of how much budget of computation you have. So that's another point that I wanted to make. And again, perhaps at that stage is not terribly clear what does it mean. So, but hopefully that will be demystified shortly. Okay. Now, I stated our result. Here's something that we would like to be able to show, but unfortunately we could not, which is, number one, it would be nice to show that the global stability, in the way I described, is also undecidable when x, the starting point, is not part of the input, because that's really the problem that the community typically looks at, because that's where you have the link of SRBM, positive recurrence, etc. And the second is that also showing that positive recurrence of SRBM is undecidable as well. Now, under the assumption that the covariance matrix is non-singular, if you allow me to make it singular, then I can make it an undecidable problem as well for almost a trivial reason, because there will be a particular path, and I will make sure that my Brownian motion only lives in this particular tiny path. But then you have multiplicity of invariant states. It's really not right question. The right result would be to show that it's undecidable when you have non-singular matrices gamma. But unfortunately, we don't have these results yet. At this stage, we have to have a starting point as a part of the input. Any questions or comments?
Possible to say, just in a few words, indicate why these are different problems, or what goes wrong with the same?
Yes, so basically, again, jumping ahead, but that's okay, let me sort of say a few words about that. The main tool for establishing undecidability is to take a given, some known undecidable problem, and build a so-called reduction. It's going to be sort of a mapping from the known undecidable problem into the Skorohod problem, such that the known problem is undecidable, and Skorohod problem is stable and not stable if and only if the underlying problem has a yes or no answer. Right? So it's like build some kind of a gadget. When we build this gadget, we will build it such that it only works. So here's what happens. If x is not part of these things, then there are certain trajectories of the Skorohod map which corresponds to absolutely nothing in the underlying undecidable problem that I will use. And therefore, I cannot make the state. I need to be able to control the dynamics for the full Skorohod problem rather than Skorohod problem with a specific choice of x. I don't know if that's answers. Perhaps that will be clear a bit later, but that's basically what happens.
If that's another question. So are there examples of other probabilistic problems that are known to be undecidable?
Probabilistic problems?
Yes, the second thing is, SRBM is a
yes,
probabilistic object, whereas the other things are sort of deterministic.
Correct. So there is one thing that comes to mind is this something called probabilistic automata. And let me come back to that when I discuss, because I have a list of undecidable problems.
The answer is yes.
The answer is yes. The answer is yes, and this is actually interesting because it has to be a genuinely probabilistic automata. If it's a deterministic automata, it's decidable, no issues. So it's But of course, it's not of the same flavor as this problem. Okay. Just a quick word that this is sort of a part of the series of papers that I and my student worked. The most, perhaps more recent and perhaps most interesting in some ways, because it's most relevant to the other models considered in the literature, is that stability of multi-class Q networks under buffer priority policies undecidable. There we make some simplifying assumptions such that, well, it's a deterministic network. We assume that some processing time can be 0, finite buffers, and so on. So it's not sort of as complete, but fairly sort of complete. It's fairly convincing, I think, that these problems are undecidable. But for now, let me stick with the Skorohod problem. Just wanted to say that this sort of a sort of ongoing effort. All right. All right, now we switch gears, and now let's forget about Skorohod problem, and let me attempt, in the remaining time, to give you a little bit of a background and some historical references about the notion of decidability. So, all right, so first of all, what does it mean to be able to compute something? Well, it turns out that there is a way to formalize the notion of computation. Usually we think, in our life, we think of computation as writing a certain program which runs, right? It might terminate, it might enter some loop or something like that. But that's perhaps how we sort of in everyday life think about computation. Well, it turns out that there is a sort of unifying way, which is computer system independent and language independent, to think about the process of computation, which is called the Turing machine. Turing machine is an abstraction of the process of computation. And we would say that the Turing machine can basically, it's like a program. It can give it can have several possibilities. It might run forever, and that's not good. And it might stop, and when it stops, it should give you one of the two possible answers, yes or no. All right? And I'll come back to this yes or no shortly. So we say that we have an algorithm for a given problem, and I have to also explain what is meaning given problem. We have an algorithm if we can build a Turing machine which never cycles forever, always holds, and always produces a right answer. Right? And let me now sort of get into a little bit of a more level of detail. So from now on, I will say that deciding or computing, it means the existence of an algorithm which terminates in infinitely many steps and correctly solves the problem. All right. So here's a way to think about it. A way to think about the problem is a collection of instances. Let me call it calligraphic A. Collection of instances is going to be countably infinite because I'm going to only consider rational inputs. Think of A as something like all the matrices, 3 by 3 matrices with rational entries. That could be an example of A. Or something like all these integers. Or something else. It doesn't really matter what it is. It's a countably infinite collection of instances, which I can encode in 0, 1, finite set of 0, 1 bits. I can take a given matrix and encode it with 0, 1 bits, right? We all can do that. All right? So we say that we have an instance if we have this countably infinite collection of elements plus some kind of a function which maps them into yes or no answers. So what does it mean? For example, if A is a collection of matrices, think about the mapping which says yes if it is non-degenerate and no otherwise. That could be an example. Or something like it's yes if it is the first entry is positive and no otherwise. Or anything like that. Really doesn't matter. It's a function phi which mapping instances into yes or no. Typically, the pair of A and phi and F phi corresponds to some kind of a decision problem that you want to solve. Like, if I have a matrix, I want to figure out, is it degenerate or not. That would be an example, all right? But this is not, perhaps this is where we're getting a little bit philosophical. This is not about humans knowing or not knowing what's the answer, so on. This is defined completely mathematically as a collection of instances and a function. All right. Now we call such a pair decidable if one constructs a certain Turing machine which does the following. So I will write it symbolically, but hopefully that helps. So we have this collection of instances, A. And we have a Turing machine. I haven't defined what the Turing machine is, but I'm going to define something called counter machine, which is actually simpler. At that stage, you can think of T as a function which maps any input X, well, we call it A, so they'll confuse into something. And the possibilities are T of A is, let's say, infinite loop, which means that when you operate this Turing machine on this input, it will run forever. That's one possibility. Or it holds and gives yes or gives no. In other words, for a given Turing machine and a given collection of instances, you can think of T as a Turing machine as a function on a set of instances, which gives one of the three possibilities. All right? There's really, you could think of T as a collection of functions or operators, like, I don't know, linear operators. We deal in mathematics with such things all the time. So there's really nothing which is described in one particular way. So we have a mapping from T, which maps A into these three possibilities. Infinite loop, yes or no. Of course, A itself is partitioned into yes or no instances. Some of it is yes, some of it is no via this function phi. I don't care about Turing machine which enters infinite loop, that's not interesting. And I don't care about Turing machine which gives me wrong output. I want to construct a Turing machine such that T of X equals, I say X, huh? I wanted to say A. T of A equals phi of A, which just always stops and always correctly classifies the input. So if this is a collection of matrices, I want to build a Turing machine such that when a matrix is non-degenerate, it will say yes. If it's degenerate, it will say no. So it's really about the sort of a functional representation of this partition of A into yes and no instances in some via a certain class of operators T. I haven't defined what it is, but mathematically it's a particular restrictive set of operators. That's perhaps a way to think about it. Okay. So we say that the problem is decidable, the problem being A and a phi. So A and phi is decidable if and only if there is a Turing machine which solves this, never loops, and gives the correct output. That's it. So, and this is why it's completely mathematical and rigorous notion. There is nothing philosophical and tricky here. Think of it as a sort of an attempt to classify and represent a partition of a particular countably infinite space via a restrictive set of functions T. So we say that pair is A phi is decidable if you can construct a Turing machine. Okay? Otherwise it's undecidable. Okay, so this is the only bit of philosophy. This is the only bit of non-rigor in this. But by the way, everything I'm describing here, of course, is that's a classics in the theoretical computer science, and I'll give you some references, interesting references shortly. Here's something which is actually non-rigorous, but I think it's a very profound fundamental statement in the theory of computability that I wanted to share it with you. Those of you who are not familiar with it, it's something interesting. It's called Turing thesis. Church-Turing thesis is not a theorem, it's a particular belief. The belief is that everything which is computable using a Turing machine. Basically, in other words, what it says is that let's define things which are computable as those classes which are recognizable by Turing machine. And the reason is that at least in 60 or 70 years that this theory, since it was developed, nobody was able to come up with something bigger, more interesting, that would be able to classify this and yet would be sort of constructive in any meaningful way. So in other words, we have this class of Turing machines, functions. And they have certain power, and this power is limited. Perhaps there is something bigger out there, which is still constructive in any meaningful way. Nobody was able to come up with such something bigger and still constructive in any meaningful way, and therefore we believe, and therefore we just take it as belief, is that computability is equivalent to building a Turing machine. All right? So that part is that statement, that thesis is not provable. It's just a convention that constructive means Turing machine. All right. Any comments? It's a opening. It's a
definition of computable. Definition.
Huh?
Its definition for all practical purposes.
It's a definition for all practical purposes, correct? For historic reasons or for whatever other reasons, called thesis. Because it's not, a definition is, for practical reasons, it's a definition. There is something more to that than definition, which is that you can define it like stability. You can say global stability in this, we can write in one paper here, one paper there, which is different. Here, there's no other definition which serves the purpose. That's why I guess it's called thesis. But in practical terms, definition, it is really a definition. Okay? All right, so let me begin to illustrate. I already gave you one example. Give you some a set of examples of decidable properties, and some of them are trivially decidable. Even though I didn't say what a Turing machine is in the end, but think of it as something. Think of it as a program. All right? So, for example, if I give you three numbers, x, y, and z, that's my collection of A. And yes instances are those x, y, and z such that z is equal to x plus y, and no is otherwise. And I want you to build a Turing machine which classifies those. Okay, that's not too hard to build a program, one line or something, which checks for any three numbers whether they match or not, right? And they will terminate in finite time. In fact, linearly, but who cares about that? Finite time, that's the important thing. So that's a decidable property. Something closer to this talk. A matrix is completely S. That's a decidable property. You have strict inequality there, so you might feel that there's something fishy, but you can deal with that. And let me not. In fact, you can. No. So remember, matrix is completely S. If A were principal diagonal, principal submatrix, you can find a vector non-negative such that the product is positive. You can check that for any given matrix. You can write a program which will do it for you. Now let me get to this point and try to explain why, when class A is not countable but just consists of one point or finitely many points, why the problem becomes trivially decidable. Let me build a Turing machine for that. But you won't believe me that it's a Turing machine, but it is a Turing machine. So let's see if this confuses you, or where is the eraser? Okay. In fact, let me do it here. So I have this collection A, which is a singleton. A. All right. This collection A has to be split into yes or no instances. Well, there's not that many choices. So let's say it's yes. Okay. So here's a Turing machine. A Turing machine will take an input, this one, and produce yes. And that's it. it will just check whether this input is indeed this input and produce yes. It's just a checking that this instance is really the instance you're talking about. Now, I'm not saying that I can do as a human, I can do that. This existence of a Turing machine is an existential statement. It means that there is a way to map it into right answer. And indeed, T maps A into yes.
It doesn't need to check anything. It just
It does
build a machine that outputs yes. And you've done it.
Yes, correct.
That's right.
Well, yes, if you define your Turing machine so that it always takes as an input correct set of it, because it might have some garbage input, but yes, yeah, you're right. So, I mean, you can just say yes, right? The important, so perhaps the following analogy would help. I think of Turing machines as a class of functions, as a certain class of restricted class of functions. Now we know that, for example, that a space of continuous bounded functions you can approximate by polynomials. So you might think of Turing machines as a bunch of polynomials, for example. With this space of representation, you can approximate any continuous function, but you cannot approximate, let's say, a Dirichlet function, something like that. So that would be a sort of analogy. But when you talk about one point, you can approximate one point with any function. So I don't know if this analogy helps or confuses you, but that's rough. So it's a theory, and even if I have a finite collection here, let's say I have a finite collection, is let's say K, then I have a whole bunch of instances, let's say AJ are yes instances, and B1, Bm are no instances. Here's a Turing machine which will solve it. It will it will just figure out what is the instance. It will just look at the particular instance. If it is one of these instances, it will say yes. If it's one of these instances, is no. Turing machine can recognize the instance. That perhaps is not so obvious, but it basically would say that I have an input string here, and it would say that, let's see what this looks like. Is it matching this one? No, throw away. This one, this one, this one, with this one matches this one, then say yes. And same here. And I will build it in such a way that it will not take input as some garbage, as James was saying. This is perhaps not completely obvious, but as it turns out, so the conclusion is that you cannot have a decidable or you cannot have undecidable properties about finite collection of instances. That's the thing. You should always talk about countably infinite collection of instances. That's the only domain where this notion of undecidability makes sense. Okay, something silly. MM1 queuing system is stable if lambda is less than mu, so that's obviously a decidable property. But going back to this one, the stability of three-dimensional Skorohod problem is decidable. And what's the algorithm? What's the Turing machine? This. I already showed it to you. This is precisely the algorithm for checking stability of a three-dimensional Skorohod problem up to three dimensions. All right. So then the natural question is, what are the undecidable properties? The fact that there are problems which are undecidable, in other words, you can build some countable collections such that no Turing machine will do the trick, is not too surprising, because as it turns out, you can prove this statement existentially. You can show that the number of things in here is uncountable, number of Turing machine is countable, so you will have a mismatch somewhere. So that's almost like trivial proof that there are undecidable properties. The question is, are there interesting undecidable properties?
You mean the number of functions that take value 0, 1 on that counter is uncountable?
Number of... No. I'm saying the number of instances. Number of problems here.
Yeah, that's right. But the problem consists of A and P.
Yes.
So
which is a partition of A. So you think of it as A.
So have countably such fees, that's what you're saying.
Number of fees is countable for a given A, but number of A's is uncountable. because it's A is a countably infinite set of finite strings. So it's a has H1 LF1 cardinality. So, but the
Why is the number of possible phi for a fixed A?
Oh, it's subsets of no, I take it back. Of course, it's a number of subsets of a particular countably infinite set, so it's uncountable. Yes, yes, you're right. You're right. Yeah, we did. I apologize.
Okay.
That's what you were saying. Yeah, I apologize. Yeah, indeed, you don't need to look into. You can take any countably infinite sequence and just say that, well, the number of possible partitions is uncountable, number of Turing machines is countable, therefore some of it is not decidable. But the question is, are there interesting problems which are undecidable? Now, the first, the sort of the atom of undecidable property is something called the Turing halting problem, but it's a bit convoluted, and let me not even describe what it is. I'll describe shortly, while I'm already running out of time, the counter machines. And this is a simplification of Turing machine, and that's where things become decidable. There's a whole variety of other undecidable problems, something called post-correspondence problem, tiling problems, Conway game of life, etc. And rather than just elaborate on that, let me just tell you that, just a second. So give you a couple of references. Specifically, the second reference is this article in AMS Notices, very nice article on undecidability. It's called Can't Decide, Undecide. So it's a very nice and enjoyable article. So, and it's like February issue of, March issue of 2010. And the background for decidability you can find in the book by Sipser, which is actually an undergraduate text in theoretical computer science. It's really, once you start looking at it, you realize there's nothing really complicated mathematically to understand. It's really not that complicated notion. It's a change of mentality in some ways, but the underlying mathematics is fairly simple. Okay, so, and to me, the most surprising thing is that, and perhaps the most natural undecidable problem, come in the theory of, in the control theory. And this is where you can really get undecidable problems which look completely benign. Let me just illustrate on the board one of them. I think it's, after I describe that this problem is undecidable, you believe that anything problem can be. So the problem is like this. So the data is, so you have a number of dimensions. You have a vector in RD, and you have two matrices, A and B, and also in the dimensional matrices. And you look at the following dynamical system. Xt plus 1 is equal to A times xt if theta dot product xt is positive, and equal to B xt if it is negative. In other words, you have a hyperplane, and you apply the following piecewise linear control. Whenever you're on top of the hyperplane, you multiply your vector by A, and if you're below, you multiply it by B. And you just keep doing it. And you ask, for example, when is it true that trajectory converges to 0? Right? Well, it turns out that this problem is undecidable. Looks extremely benign. You would think that something which has to do with eigenvalues, spectral radius, things something like that should do the trick for you. But yeah.
So here it's undecidable even if D is fixed, right? Which is different from your previous statement.
I think it was first shown for general D. Maybe it was, but then I heard that it was fixed, solved also for a fixed D. That's possible. I'm not sure I have a reference for that. My reference is this survey paper of '99, which might not be up to date. I think it's possible and quite believable that it's even with something like D equal to 3, it's undecidable.
Sorry, I didn't catch the statement of what the function phi is.
Oh, okay. So now you have a triplet theta, A, and B. And let's say this triplet is yes instance if every trajectory goes to 0 and no otherwise. If I'm not mistaken, it's this. Alternatively, you could also put a starting point as a part of the input. But to be honest, I don't remember for sure. Is it a global stability or stability with a given point? But
I guess there must be some relationship to provability. If this is undecidable, it must mean that infinitely many of these things, there's no proof of whether it's...
In fact, yes. So this is this is something that I skipped in the interest of time. But it turns out that there is a deep connection between undecidability and Gödel's incompleteness theorem. Gödel's incompleteness theorem means that certain statements are correct but not provable, whatever that means, right? But it turns out that there is a connection. For example, the famous logician Klein showed that you can prove Gödel's incompleteness theorem from the undecidability of Turing-Kolchin problem. So that there is this direction. So once you know that this problem undecidable, he managed to show that Gödel's incompleteness theorem is implication. Gödel originally proved it using different means, but they all have this similar flavor. So
does it go the other way too?
I have my knowledge of Gödel's incompleteness theorem at the level of Wikipedia. So I only found this one direction, and I'm not sure that there might exist the other direction as well, but I'm not sure about that. So maybe you can find out right now. Moving on. I have practically no time remaining, and I wanted to plan to show you a lot of things. Let me perhaps just describe this slide. Say one word. Why the try to answer Maury's question as why the dimension is unrestricted in my case, and then wrap the talk, because I apologize, I'm running out of time. Here's a device which is very similar in flavor to Turing machine, but it's actually much simpler. So the device consists of the following things. It consists of states. Let's say in this case it's 3 states, S1, S2, S3, plus 2 counters. Each counter, you can think of it as a queue, contains non-negative integer. And at every step, in integer times, we're going to update counters and we're going to update states. So time 0 state is 3, counters 1, 1. We're going to keep changing it. We're going to change it according to the certain rules, collection of rules, which is given by the following finite table. The table means the following. You take a state, you look at the counters and see if it's positive or 0. Never mind what's the actual value if it's positive, but positive or 0. And do the update accordingly. So, for example, basically it would look like this. So we start with S3 and 1, 1. Then we need to update it. How do we update? It says S3, 1, 1, 1 is positive, 1 is positive. It says that go to state S2, don't touch the first counter, add the second counter, 1 to the second counter. So the second configuration would be S2, 1, 2. And then you update this one. S2 is again S2 plus plus, so you go here, state 1, 0 plus 1, so it's going to be S1, 1, and 3. And then you keep going. That's a very simple dynamical system. You just keep going. All right, what do you do with that? You ask the following question. You start with a particular configuration and you ask whether you come back to it. Or if you have 2 configurations and you ask, can I start, if I start here, do I ever come back to something second configuration? Well, lo and behold, this turns out to be an undecidable problem. And this is a very convenient statement because I can now try to take the statement and embed it into the problem of interest and show that that problem of interest is undecidable as well. And that's perhaps the even less interesting sort of, now you have to be just clever enough to do this kind of reduction. And I don't have really time to do that, but basically sort of at high level looks like this. Now remember in 6-dimensional matrix that Maury had for his counterexample, look how crazy is this. So you have, the drift vector is simple. It's -1s and 0. You have 5 -1s, everything else is 0. Then you have this complicated matrix. Somewhere in this matrix, these updates of the Turing of this counter machine SID. And again, I don't know how interesting are details, but it turns out that in the particularly matrix which corresponds to BE, you encode the updates of the states, and the matrix CE you encode the updates of the vector. We build this embedding in such a way that when the machine is in state, say I star, a particular sub-vector of vector G will have this configuration. That's why, so the dimension of Skorohod problems is bigger than the number of states. For counter machine, I have undecidability only when the number of states is not bounded a priori. That's why I don't have a fixed dimension result. I don't know if this answers the question of why this particular embedding is such that if counter machine has dimension, counter machine has m states, the Skorohod problem will have dimensions something like 5m plus 9.
So the counter machine you showed us earlier with 3,
it was an example of 3.
The class of problems encoded by this thing is decidable
For
a particular number of bits.
actually, well, here's the thing: if the number of states is only 3, and if you look only about coming back to this configuration, let's say S00, you're dealing with a finite collection of instances, so it's decidable trivially. So that's why counter machines you need to keep unbounded, no bound on the number of states, and basically, all right. So no point perhaps to give you details of that unless you're interested in offline. I can elaborate on that, but that's the last part of the talk, and perhaps in a way least interesting, because it just says that yes, indeed, you can have a convenient undecidable problem and embed it into the problem of interest and do it. But of course, the technicalities are important and difficult. And yes, Maureen?
How hard is the proposition?
Which one?
The one that you were citing in order to this statement undecidability
of counter machines? Yeah. So, well, first, before I answer that, the beauty of this theory is that you don't need to be a specialist of this theory in order to use it. So I don't even need to know what the proof of, right, why the counter machines are undecidable. I just need to know that that's a fact and embed it. However, it's not too complicated. You can reduce it to Turing-Halting problem by doing some kind of a representation of, you take integer numbers and you present it as a product of primes with exponents, and these exponents are values of the counters, and you do some tricks. There is a book by Hopcroft and Ullman in 1970 where there's the details of that. So you reduce it directly to the Turing-Halting problem.
I mean, is there some place where some heavy lifting has to be done, even if it's results based on results, or is it just showing an equivalence to the Turing problem, and there's never anything that's particularly complicated?
Or what was the first problem that was shown?
Yeah, even the first problem was not too hard to show. It's a diagonalization argument to show that Turing-Halting problem is undecidable. The genius of Turing was to recognize that such a thing is possible. Now, I'm saying that the last part is non-interesting. Perhaps I should be careful. It's actually very non-trivial, difficult sometimes to build this reduction. It's completely non-trivial thing. It took us quite a bit of time to build this reduction from counter machine. This is where the heavy lifting is. But conceptually, it is perhaps less interesting. I wanted to focus this story on the undecidability rather than, I could just tell you about how you build the construct. You just build this particular map, and then just simply follow that whatever the updates of the counter machine, you have exactly the same updates in the Skorohod problem. And then you do it in such a way that Skorohod problem converges to 0 if and only if the counter machine repeats the state. I'm out of time, so perhaps I should stop, but I'll be happy to take questions, well, now or offline. Yes.
Thank you, David, for interesting talk. So I think that I would suggest the following, that yes, everybody who is, so we will finish officially we are out of time, so but if you want to stay, you may stay. If you want to leave, you may leave now. Let's continue with questions.
Yes, but obviously I'm happy to answer.
Yeah, Jean, you have a question, you may ask it, we will continue, but everybody's free, whatever, yeah.
Yeah, thanks.
So you may ask a question.
My question is, the whole stability of the fluid model, it looks really a lot like this piecewise linear, the stability of the piecewise linear system. In fact, you have piecewise linear except on subspaces of different dimension, you change the matrix. And so isn't it possible to have some direct reduction to the model of piecewise linear?
I'm not sure I understand. So the Skorohod problem a priori is piecewise linear, right? So there's no this z and y.
You mentioned this problem, which is known to be undecidable, which looks a lot like the problem with the stability of the fluid model. Isn't it possible to have
embed this problem? Perhaps it's possible, but we couldn't do that. For some reason, for all the prior works, we use the counter machine, because the counter machine operates by looking whether you have zero or non-zero encounters. And that's very much like in dynamics of Qs and dynamics of Skorohod problem. This one is more like, if you wanted to prove an undecidability of something like processor sharing policy or something like, perhaps something like this would work when you say, is my buffer bigger here than here, and this. We couldn't embed this particular problem, but of course, it's not to say that it's impossible. Yes, Ruth.
Related to that, you know, there are solutions to the Skorohod problem where in a finite interval of time, you switch the piecewise linear directions infinitely many times. So it's not just finitely many piecewise linear pieces.
Yeah.
And that may be why you can't.
Yeah. Yes, Damon.
When people prove undecidability results, do they pretty much always prove equivalence to the counter machine or something equivalent to it? Or is there a whole range of qualitatively different undecidable problems?
Second. Right. So there is a whole range of problems, and sometimes one problem doesn't do a trick for you, and all of a sudden the other one does. That's why it's important to keep a whole range of problems, such as post-correspondence problem, tiling problems, game of life, and so on. That's I think partially this is answered in this AMS article, but yes, it's as far as being able to prove something, it is important to look at the. I don't know if they are qualitatively different in the sense that they're all Turing complete. So, and whether you can say something beyond that, I'm just not sure about that. Yes.
Asking if something iterative hits zero and stays there is an undecidable problem. But like I guess, but this is a guess. But asking if something hits in a finite bounded interval would be decidable just to run it with say capital P steps and then ask it for this
finite bounded interval? Yes, bounded interval. Yes.
Does that extend to the fluid question? Can you say in a compact interval it will hit zero and stay there? So if you run into the data time interval which you specify the time interval which you want to hit it. Is the question still undecidable?
I see. If the I'm not sure. I haven't thought about it. If the data is integer and all is such that all the updates are, if the data of the matrix and the drift are integers, then probably the answer would be no, because and if the dynamics was unique, because I don't want to, let's say, not dealing with non-uniqueness issue. But if it's unique, then I can simply look at the integer steps and then figure out whether it hits zero or not. But if you have, but I guess I can assume that the data is integer by rescaling the problem appropriately. So I'm not sure you can actually build something like that. But I haven't really thought about that carefully.
That's a good question. So you are dealing with R that is completely S. That's the background assumption.
Indeed, when we build the matrix, you can verify.
Sure.
You can verify that this matrix is completely S.
Right. Now the question I have is, maybe that's to Ruth, is whether given any completely S matrix, we can find a multi-class queuing network that results into something like that. You know, do we have a physical representation? Or, I mean, how realizable is a completely S method in general?
Yeah, I understand the question. I don't think
if
I have
it
an
is
answer.
identity minus a transpose of the
Yeah.
stochastic method with largest eigenvalues more than 1.
Well, it depends on what is the richness of the class of Q models you will
Yeah,
use.
yeah, that's,
What
do we know
policies?
this answer? Do we know this
So,
answer?
no, I don't.
Because if we did, then we would ask the question, is it decidable within the class of R matrices that come from multi-class queuing networks or whatever?
Well, okay, so for multi-class Q network, we show that, for example, operating on the priority policy, it's undecidable. So, but of course, you can come up with the smaller classes or different classes where things are nice or product form.
And one comment, since you mentioned Matyasevich, 1970, there's another article, I think, a year ago in the Notice
That's right.
about,
Right.
you know, the
Absolutely, yes.
particular polynomial with integer coefficients whose range is precisely the prime numbers, this kind
Yes.
of thing.
Yeah, it's a beautiful, and that's a sort of a pinnacle, and this is certainly a jewel of this theory,
Yeah.
that Matyasevich 1970 paper, which shows that you cannot have the problem of figuring out whether you have integer solutions to a polynomial, multivariate polynomial, is undecidable. Because if it was decidable, you don't need to prove the Fermat's theorem.
Right.
You just need to build the right Turing machine and use it. That was sort of why it's so important that it's undecidable. Therefore, you really need Wiles's and the Wiles's of the world too.
Yeah, and Matyasevich actually showed that there exists such a polynomial, for instance, but then people came up with concrete polynomials many years later.
Yeah.
In fact, it's supposedly so simple. You can find the article in the American Mathematical Monthly. The polynomial whose range is the prime numbers precisely.
Yeah. So,
Okay, thanks.
thanks. Yeah.